Já se budu snažit. Já se budu snažit to udělat. Hodinu a půl mi bylo řečeno, tak jsem... Jo, dobrý. Tady. Boběstědo. A co? Jenom kolik tak mám začít? Nebo je to? Už jsem pochopil.
Dear colleagues, just before we start, I have one organizational problem. Here we have the attendance list. Most of you have those three of you did not sign yet. So brief. I will put the attendance list on the desk at the top. So please, because of sponsors, we need all of you who are here. Okay, so dear colleagues, ladies and gentlemen, let me welcome you again in Ostrava. I'm happy that this difficult situation, so many of you came to Ostrava. I hope that you are enjoying staying here. I hope that you enjoyed the problems today. And really, it is my very big pleasure to welcome here in Ostrava Pískovský. Vítek was a competitor on our competition 7 years ago. Then he moved to Cambridge, and after receiving his Master of Science, he moved to Oxford, where he is doing, and I hope that successfully, he will do his PhD in applied mathematics. And today he will show you some of his results, some of his research, and it will be on topic from mathematics to biology and back. So please, Vitek, it's yours.
Hello. Hello, everyone. Thank you very much for welcoming me in here. It's a great pleasure to be here because it's coming to my hometown. I'm originally from Ostrava, and so this is really a personal place for me. I sort of started doing mathematics pretty much in this location when I was walking to school with my grandpa, who is sitting here, and he chatted to me about mathematics. And I really got inspired by this, and I really enjoyed it, and it sort of continued because I was in the city. I took part in this competition, and then continued with it. Went to study it at university, where I studied pure mathematics for first 2 years. But then I sort of started engaging a bit more with applied science. I started engaging with biology as well. Well, to be more precise, I got engaged to a biologist. And so that's sort of how I got interested in biology a bit more. And now I'm in Oxford, working with 2 people, Philip Miney, who is a director of the Wolfson Center for Mathematical Biology. So Philip is sitting in the Mathematical Institute, and Kevin Foster, who is an experimental microbioecologist and evolutionary biologist. And so with him, I'm learning a bit more about biology as well. And so these 2 people sit in different buildings, and a lot of time I need to go from the maths department where my office is to the other department, and then I need to go back. Often I go there to the biology department. I realize that the meeting I thought I should have today is not happening, and then I just go back. And so when I was asked about the title, I thought it would be appropriate to call it From Mathematics to Biology and Back. And so that's what I'll be talking about to you today. So there are many areas of biology where nowadays you can use mathematics and apply mathematics to it to help understand the problems ranging from developmental biology, cancer biology, to neuroscience, to evolutionary biology. But today specifically, I would like to focus on ecology. Maybe just to get an idea, how many biologists do we have in the room? Okay, that's great. How many people who are mathematicians but heard about mathematical biology as a topic? And how many have done course in mathematical biology? Are there any people? That's great. That's amazing. Because I was scared that I would be just teaching you the basics that you have all seen if you have taken a course in mathematical biology. And then I was, well, I'll try to start with the basics and then get to the cutting edge research that is now happening. But okay, that's good. So I'll try to also sort of try to explain all the basic concepts, both in mathematics and biology as we go on. So what is ecology? Ecology is primarily study of organisms and interactions between them. And sometimes these interactions are very intricate. This is a very recent paper from Science. And in this study, they noticed that there is an invasive species of ants coming into a savanna ecosystem. And you would think that's a small ant, nothing will happen really, right? But what happened is that this invasive ant managed to outcompete the native one, but the native one produced a toxin. And because it produced a toxin, when elephants came to the tree on which the native ant was, the elephant wouldn't normally graze on that tree. And so there would be enough of green space. But when the invasive ants came, then the elephants were not afraid to eat that tree, and they ate the tree, and there was not enough of green space. As a result, lions didn't have enough hiding space. And it was much more difficult for them to predate on zebras. And so there was a complicated consequence of ecological impacts just from single small animal species coming into the ecosystem. This just to sort of tell you how complicated and complex the things can be. And well, in mathematics, what we often do is that we are very good at forgetting. Don Zagier, a German number theorist, often says mathematics is the art of forgetting. And so it's sort of challenging, right? You have very complicated system, and what we want to do in mathematics is to make some abstraction of it, but still learn something useful about it. And I would argue that even in biology, what you often do is forgetting. You go and start with something simple, and that's what we'll start with. We'll start with population ecology. We'll start with thinking just about single population. And ideally, to make it even more simple, let's imagine we have some species in controlled experimental setting where we can control the environment. So the data that you would be able to collect as a biologist is probably the abundance of that species over time. And as a mathematician, you may try to ask what patterns do we see in these scars and how can we try to understand them? So this is the simplest take on the problem. You would just model it as a differential equation. And you would imagine that the number of species changes proportionally to the number of species that there are at some constant reproductive rate R. You can easily solve this equation. What you get is an exponential growth. This can be a good model in some cases. For example, if you have E. coli or other bacterial species growing in well-defined media, what you'll see is an exponential phase of growth. After some lag, they need to sort of readjust their enzymatic machinery to be able to eat the nutrients around them. But once they are able to do that, they grow exponentially until the nutrients are depleted. And then they enter into a stationary phase. Well, that's not what we see in this model, right? According to this model, bacteria would eventually invade the entire planet. They would sort of blow up. So the simplest way how we could account for some sort of maximum number of species that the environment carry is by introducing some idea of carrying capacity and density dependent growth. So maybe if there is more species, you can't grow that easily because you'll be competing for resources with them much more, and you can't grow that much. Mathematically, it's just as if we took the constant growth rate and modified it to be a linear function with negative dependence, so that as n increases, the growth rate linearly decreases. You can solve this, and this is how the solutions would look like. And so in this case, the dynamics would approach a equilibrium. And so this is the prediction you get. Actually, if you took an arbitrarily complicated differential equation of this sort, what you would get is still, you would see stable ecological equilibria, stable fixed points of this equation, right? So you do, as mathematicians, the usual analysis, you find the fixed points, there's the points where the derivative is 0, and then you can look at small perturbations around it. Once you plug that into it, you would see that the perturbations grow proportional to the derivative of the forcing function. And if the derivative is bigger than 0, the fixed point is stable, otherwise it's unstable. If you draw a diagram where you plot the function f, you can see the intersection points as the fixed points, the red dots, and then the abundance, if it's, for example, in this region in here, would go towards this fixed point. There can be possibly multiple sort of ecological equilibria, multiple fixed points. But altogether, with differential equations of this form, what you always get is an convergence to some equilibrium. Now, let's think about some specific problem now. This is Australian sheep blowflies. They are quite nasty parasites. They can go into sheep while they lay their eggs in the sheep's skin. The larvae grow in that environment, damaging the sheep's skin, can cause inflammation. Sometimes the sheep can even die. Then these larvae drop to soil and they become adults. Process continues. It's quite a big problem in Australia, and for that reason, Nicholson in 1950s decided he'll study this. And so he took the simplest possible case. He took a cage, put there some sheep skin, kept it at constant levels over time, and tried to keep all the other environmental parameters like temperature at constant levels. And then he watched how many of adult blowflies he will see. And this is what he saw. Something completely opposite to what you would predict from any differential equation. You'd see quite persistent oscillations in here, up and down in the density. And that's sort of where mathematics and biology disagree. And this can either be a starting point for frustration, or as my supervisor Philip says, it's where the exciting things happen. Because that means that probably we should try to be more inventive with our maths and try to come up with some better model. And so let's try with the simple approach. Just make it specific to this model, like before, just simple differential equation. And so in this equation, we will have number of species reproducing at some density-dependent growth rate R, proportional to how many there are. And we will take this growth rate to be composed of two things. Firstly, the egg production. And also, if there are too many other adults, it will be firstly, more difficult to find spots to lay more eggs. Also, as a population, you would not need that many more individuals. So we can imagine that there be an exponential decay with the number of sort of reproducing adults, and there will be some constant death rate. You can also argue that this should be the case from the data they collected in the lab. And if you make the model as before, we can plot the total growth, that is this function. We can find the points which are fixed points. We can analyze the stability. We'll see that provided that there's more X produced than individuals that die, then there'll be a stable equilibrium. And that's not what we see in the data, right? So how do we go about this? I think this is quite an ingenious idea. The idea is to think about a delay, because once the eggs are laid, it takes time, usually several weeks, before they become mature adults. And so there's a delay between producing the eggs and then becoming an adult and possibly by that time dying. And so we can think about introducing some time delays into this equation, and we get to completely different mathematical work of delay differential equations. And we can start to think about how that affects the stability. Just to make our life a bit simpler, we can sort of rescale variables so that we have this equation, which has the same dynamics, it's just with rescale. And again, provided now B is our parameter of production over death, so that's sort of the effective net production that is sufficiently large, then we get, I think that should be bigger than 1. Sorry. There will be a fixed point that is, well, there's a question, is it stable or not? And so to do that, we'll do the similar analysis. We'll take a small perturbation around this fixed point, plug that into the equation, linearize it, and this is the equation for the perturbation. And then we ask a question, is this perturbation going to decay or not? And because of the linearity of this problem, the initial condition, which now is not just a condition on single time point, it must be a condition on the entire interval between the delay and 0, can be written as linear combination of solutions that have this form. And so we can plug this in and look at solutions to these equations and ask whether solutions to these equations, which are complex numbers in general, have negative real part, because if they do, these will correspond to decaying perturbation, so the fixed point will be stable. If there is at least one solution to this equation that has positive real part, that means we'll have a unstable ecological equilibrium. And so that's how you can do the analysis. You can sort of try to think about these solutions, and in some special cases, for example, if A, which is now the rescale delay, that is 0, we recover again that the fixed point is stable. That's what we got before. And then pretty much for almost all other values, we can express these solutions in terms of various branches of Lambert W function, which is an inverse to this function. This just sort of rearranging this equation and using the definition of Lambert W function. And here we get mathematically even into interesting area of analysis of complex functions, right? This is a multi-valued function. So there are as many branches of this function as, well, integers. And we can try to plot the real part because, well, there are standard ways how you can approximate it with a power series, or how you could approximate it with continued functions and so on. And if you make a plot, you would see that different, well, in here I'm changing the delay, and there are different branches, and you'll see that as A is very small, it's close to zero, so there's no delay. That's when we know that the fixed point is stable. But when delay increases, it is possible that there will be some eigenvalue that goes above this line of zero, which means there will be instability, and maybe the fixed point is no longer stable. And we can try to analyze when this happens, when there is this sort of loss of stability. And so when that happens, the solution to this equation is pure imaginary. And so if we just make this, well, ask this question, when a pure imaginary solution solves this equation, we can just try to rearrange things and compute that that happens when A reaches this value and omega squared equals to this combination of the value for the fixed point. What we see for that, it is necessary that this fixed point must be bigger than 2, because otherwise there's no solution to this equation, and sort of this never happens. And so provided that this fixed point is bigger than 2 and the time delay is bigger than this value, you can show that that's precisely when this fixed point becomes unstable. And so we can think about it now biologically. What does it tell us? If there is sort of sufficient egg production, there is sufficient turnover in the system, and there are sufficient time delays in the system, then the system, then the fixed point is unstable. And so in this case, we get into a regime where all our fixed points that we have, there's also this trivial fixed point, which is also unstable, are unstable. So what happens? If you numerically simulate it, you see these oscillatory patterns. So by introducing time delays into differential equations, you can get instabilities and oscillatory behavior even if you couldn't obtain it otherwise. And this is pretty much widely accepted explanation of what is happening in the case of Australian sheep blowflies. Now, you can ask a question as a mathematician: is this a unique mechanism that you could use to explain what is happening? And the answer is relatively easy. It's not, right? You can think of as many models as you wish, how you could get some sort of instability of a otherwise stable fixed point. Maybe you could introduce some sort of extra variables that will make the system two-dimensional, and in 2 dimensions, and we'll see this later, you can get oscillations. Or you can think more simply about it. Maybe there's a different way just to how we could represent the life cycle. Instead of thinking about it as time delay in differential equations, we could think about it as sort of just discrete generations. And then, well, we can think about the simplest model we had in the beginning, which was the logistic model. We'll just write down a sort of quadratic forcing to this discretized model. This is often known as logistic math. And what we could think is that maybe it will have similar properties as just the differential equation. Again, there will be just stable, unstable fixed point. You'll eventually converge one of them or something like that. And we can try to analyze the stability of any of these fixed points, and if any of these ecological equilibria in the same way. We find fixed points of this map and then ask, well, what happens if we make a small perturbation around it? This small perturbation to linear order behaves like this. This has a solution of this form, which means that the perturbation will grow precisely if the magnitude of this derivative is bigger than 1. If it's smaller than 1, the perturbation will decay, meaning that the ecological equilibrium, the fixed point, is stable. So that's pretty much just a variation on the technique of linear stability analysis in the case of discrete maps. Will it change the results? That's the question. So let's start by varying this parameter A. if we take A that is relatively small between value of 0 and 1, what happens is that the total number of individuals in the next generation is always smaller than the initial number of individuals. What this means quite intuitively is that the population will decay and go to extinction. If you think about it geometrically, what happens is you can plot this function in this plot, and then what we'll do is just sort of continue and iterate this map. So if we start in here, we go to this value of this function and then move back, well, record this value, and then we repeat it. And as we repeat it, we get into the regime of extinction. Okay, that's intuitive. What if A is a bit bigger? Well, in that case, now your quadratic function will be intersecting this line, and where the intersection happens, that's the fixed points, that's the ecological equilibrium. And then provided that the slope is of magnitude smaller than 1, this will be stable. And that's relatively easy, right? You can find this point. It's just like solving quadratic. You can compute the derivative, you can prove that it's stable in this regime. So let's push it even further. After a while, this equilibrium will become unstable, right? Because the derivative in here will have magnitude bigger than 1. What that means that this equilibrium is no longer stable, this one's no longer stable. And so something else must be happening. And what you can see actually is, if you try plotting it, is that there is a sort of globally attracting orbit of period 2. You start in here, come down here, and then you get back where you started. And so you get these oscillations, the same oscillations that we saw in the delay differential equation model. And you can again try to analyze it. You can actually find these points between which you oscillate analytically, because, well, you can try to think about iterating the map twice. These periodic points will now be fixed points of this map, because as you go twice, you are where you started. And so just plugging quadratic into quadratic gives you a quartic equation, but luckily you know two solutions of it. That's the fixed points. That's just the solutions of the quadratic. So you can factor them out, and you're, in principle, you can find out these two points, and you know that they are not sort of fixed points of just the map from xn to xn plus 1. So you know that these are the two periodic points. And then you can try to think about their stability, and what you'll see is that there, again, you have the slope smaller than 1, lying stable. Now, beyond that, it's much harder to make analytical progress in this way, in this fashion, because you would go and, well, you put a quartic into quadratic, you get polynomial of order 8, try to find proofs of that. Well, that's not analytically possible, but you can still try to at least ask what happens when these 2 points will lose stability, and you can see that that will eventually happen. And once it happens, there'll be again sort of another period, or, well, orbits of another period 2 coming out of that. And that's sort of a cascade of period doubling. And what happens at the end of this cascade is something that people call chaos. It's hard to sort of understand where you'll end up if you know where you started, because the map can take you pretty much everywhere. To give you a better idea of what happens there, you can go and try to analyze analytically the case when a equals 4. In this case, this map becomes quite simple. It touches the top in here, and we can relate it to a map that we can study. much more easily. And we can relate it to this map, which is called sawtooth map. And there is a transformation in between the two. So if I know a trajectory and orbit in here, it translates to orbits in there and vice versa. And so it's equivalent to actually study the chaoticity of this map because we can map one into each other. And so let's try to think about what this map does really. And the easiest way to think about it is to think about it in terms of binary representations. If you write down a binary representation of any number yn, this map takes you to a number which is just the number shifted. If you after shift end up with 1 at the place before the decimal point, you just delete it and make it into 0. So what you are getting is something that is called Bernoulli shift map also. Same name for this sawtooth map. And we can try to analyze what happens to this shifting in binary representations. It has several interesting mathematical properties. First property, it has something that is called sensitive dependence on initial conditions. That pretty much means that if there is a point standing close to you, you are a close friend with someone, you can drift apart as life goes on. There is a, mathematically, there is a delta such that for any point x and for any epsilon, you can find a close friend of x within epsilon neighborhood of it, such that eventually for some n, you will end up very far away from each other. So we can try to prove this property. Just take delta 1/4. We take n sufficiently large so that 2 to minus n is more than epsilon. And then we can think about an x that is given to us. And then we will make the first n digits the same so that we are sufficiently close to x. But then the digit after that, we will change it to the opposite value. What will happen if we'll be just shifting the digits, right? If we shift them n times, we'll end up with numbers that differ by at least 1/2, definitely more than 1/4. So two numbers initially close to each other will end up very far away. Second property that this map has is topological transitivity. If you have two open sets that intersect with this interval from 0 to 1 that we are considering, then there will be n such that if you continue sort of iterating one of these intervals, you will eventually hit a point in the other interval. It's sort of like a property of mixing very well by the map if you apply it repeatedly to a set. What this means, mathematically, to try to prove it, is that there will exist an orbit which is dense in this set from 0 to 1. And so we will not be proving this part, but we can prove the topological transitivity. For this, we can think about a point in set J1 and about a point in set J2. And then we will create a point in J1 by sort of gluing these p's after some sufficiently large number of digits so that this accent still stays in J1. J1's open, so that's possible. And what happens is that if we are shifting it n times, we'll just end up with this point y. So we end up in a point that lies in J2. Proof finished. Third property, this map has periodic points that are dense in this set from 0, from in this interval. So this is quite interesting, right? So how you would go about proving it is that you would consider any point and you would find a point close to it so that it will be an n cycle. And you can do it relatively easily. Just after n digits, you would cut it and repeat it again and again. By making n sufficiently large, you can make xn as close to x as you wish, and this will be an n cycle. And this is pretty much what defines a chaos in general, these three properties, at least according to Diveny, which is one of the standard definitions how to think about chaos. If you have a map which takes you from some value xn to xn plus 1 by some continuous function f, you can think about an invariant set. These are sets that are mapped to itself. In our case, it was the interval from 0 to 1. And on this set, the map is chaotic if it has these three properties. Sensitive dependence on initial conditions, topological transitivity, and periodic points are dense in lambda. Actually, you don't need all three properties, and that's actually a nice paper if you like mathematical analysis. Punks managed to show that if you have property 2 and 3, property 1 immediately follows. So in fact, we could just prove 2 and 3 and then use this paper. There's an alternative way how to think about chaos, because this is quite complicated definition. You need to check 3 properties or 2 properties, and can get quite cumbersome, especially if you are dealing with some, well, less behaved map. And so there's an alternative way to think about chaos. And the way how you can do it is to think about something called horseshoe. And we say that a map has a horseshoe if there is an open interval which has 2 open disjoint subintervals such that these intervals map into this interval. And then Glendining says that a map is chaotic if there is n such that nth iteration of the map has a horseshoe. Well, because we have 2 definitions of chaos, it's good to relate them, right? So what is a horseshoe visually? We have a map F that's carved, and then if you are, and then you have set J and 2 subsets J0 and J1. If you start in J0, that is mapped to J, and similar J1 is mapped to J as well, and these 2 are disjoint. Pardon? This is for this is just thinking not about logistic map, but about what horseshoe generally is. We usually don't think about A larger than 4. I think you can show that if A is larger than 4, you'll, with probability 1, leave the interval from 0 to 1. So you better think about just sort of maps that preserve your number of species within sort of the maximum of 1 and minimum of 0. And so usually people don't think about it too much because it's sort of biologically irrelevant. But you can see these horseshoes, and we'll see that not in F, but maybe in iteration of F. And that's what happens. So this is just an arbitrary sort of function F, not the logistic one, not quadratic. And we will try to show, or at least I'll try to explain to you why the first definition of chaos is implied by existence of horseshoe on some set lambda, which is an invariant set. The way how it's done is that you need to construct this set lambda, and you can think, well, I'll just give you the proof idea under some technical assumption that it is monotonic on each of these intervals. These are disjoint, and if well, some point is mapped into this interval, it better be coming from either J0 or J1. Sort of what you see in this picture is what I assume. And then you can consider this set. You can consider a set of all points that if you would iterate them and consider the orbits, they will always lie in the closure of J. Alternatively, think about it, you can just rewrite the definition of this set this way. And then it's relatively easy to check that this is an invariant set. Again, a bit of set theory. it's easy to see that if x is in lambda, you apply f, then how many times else you apply f, you still end up in lambda. So lambda is in this set. For the other way around, you need to use intermediate value theorem. It's relatively straightforward. Once you have this, you have an invariant set, and you want to prove the three properties of Divan-Eccles. And there's a clever trick to do it. The trick to do it is to sort of prove that this is symbolically equivalent to just the Bernoulli shift. And for the Bernoulli shift, we already proved that it satisfies the three properties. And so the way how we do it is that if we know that some x lies in this set, then after n iterations, you'll still be in this set, and that means that you are coming from either J0 or J1. We are coming from J0 in the previous iteration to n, you would set a value of some an to 0, otherwise an to 1. And in this way, you can map these x to these values of a. And then you can notice that acting with f on x is same as doing the Bernoulli shift. So this is sort of the proof idea. The thing about this is also quite an interesting set because this set looks a bit like, if you know the Cantor excluded middle set, it's the set with similar properties, right? It's sort of like consisting. In the first case, you exclude this middle part, then if you take intersection with sort of excluding the middle parts of these things, and so you end up with a set that is uncountable, infinite, but has length 0. But still is a set that works, so you have what you need. So let's go now back to our logistic map, and we'll try to improve our results about chaos when that happens. We can think about the third iteration of the map, and you can sort of find that if A is sufficiently large in this range, you will have intersections that are not these fixed points. And so they correspond to period 3 orbits. And this is an interesting bit. If whenever a map has a 3 cycle, it automatically has a horseshoe of the second iteration. And horseshoe of second iteration, by our previous argument, implies chaos. The way how you do it is that, well, without loss of generality, you can order your points on the period 3 orbit such that x0 is more than x1, more than x2, and then x0 is mapped to x1, x1 is more mapped to x2. So the map sort of looks like this. Well, I'm always assuming the f is continuous, as is the case for the quadratic. And then you can show by intermediate value theorem that there will be this fixed point, and also by intermediate value theorem, we can find that there's another point between x0, x1, which is mapped to the same value. We'll call this point y. Now, if we take point y and z and think about the second iteration of the map, then z is mapped to itself, y is mapped to z. So that's these 2 points. But then if we think about where x1 goes, x1 after 2 crowns ends up at x0, but x0 is definitely smaller than y, and so we get a nice horseshoe. And so period 3 always implies horseshoe, implies chaos. Now, period 3 orbits are actually very interesting. They are not just implying that the dynamics of the ecology would be chaotic. They are also implying that any other periods will occur, and that's a very deep result by Pískovský. Well, you probably have seen ordered sets of numbers before. This is probably the least obvious ordering of numbers you have ever seen, at least I have ever seen. So the biggest number is obviously 3, and then 5 is bigger than 3, 7, 9, and then once you go through all odd numbers, then 2 times 3 is a bit smaller, then 2 times 5 and 2 times any odd number. Then you go to second powers, third powers, and then you just end up with powers of 2 no odd numbers. 1 is the smallest numbers. Okay, we agree with that, right? So the theorem then says that if there is a cycle with period of k, any cycle of small period will automatically occur. So orbital cycle of period 3 will automatically imply that there will be cycles of all possible periods. So that was sort of digression going into something a bit more mathematically interesting. But now let's go and think back about population ecology. And in population ecology, the message which we sort of learned is that the population dynamics can admit ecological equilibria. And these equilibria can be destabilized if we have some delay or discrete generations and then sufficient turnover. We needed sufficient parameter A in the logistic map for the chaos and all of these instabilities to form. Also, with chaos, there's an interesting question for biology and in general modeling these sort of population dynamics, because once you have collected your data, maybe you can try to fit it with some model, but if you are fitted with some model that is chaotic, there can be a slight difference in how you measure the data. You forgot to count one individual there, and then you apply the model, you try to make prediction, but if your model is itself chaotic, just making a small mistake by counting one individual or not counting it will, after making prediction after 50 generations, will lead to completely different values of the population. So you need to be careful if you are using a model which is inherently chaotic to predict what will happen after many generations. Okay, so we thought about population ecology. We abstracted as much possible. We'll now go into something more exciting. We'll think about community ecology. What happens if there are more species that start interacting? And the easiest interactions we can think about, and people have thought about for centuries, pretty much is predate-prey interactions. This is data coming from lynx and a hare from Canada. And what you can see in this data is that if the population of hare peaks, after that, the population of lynx that feeds on the hare peaks. And as a result, because they feed on them, the hare population decreases, and this process repeats, and there are these periodic oscillations. It's not just a thing you see in macroecology. If you go into more microecology, there is quite a recent paper in Nature where they have made an experimental setup with plankton, had a species of zooplankton and a bit of algae. This zooplankton feeds on this algae, closed them there, and managed to maintain them, which I think is the hard bit in biology, for many, many days, pretty much a year. Very much long-term experiment, and then they observed these fluctuations again. If you plot it in the prey-predator plane, what it looks like is these oscillations. Can we have a mathematical model that explains it? And the answer is yes. We can have a model, and this goes back to the beginning of 20th century and to Locke and Volterra. And you can think about predators. I have it the other way around, I think. Prey is X, predators are Y in here. So prey reproduces, and it reproduces at rate A, but is eaten at rate B by predators Y. And predators, if no prey X is 0, then the predators would decay on their own. They need the prey to feed on. And then, well, if prey is present, by eating the prey, that increases the growth. So that's the model. You can try to think about how mathematically how that behaves. You can see that it has 2 fixed points, 2 ecological equilibria. One of them is trivial one, no species are present. The other one is a bit more non-trivial one. You can ask about stability. And if you do linear stability analysis in this case, it's the same thing as we did before, just with vectors. And so our derivatives becomes this Jacobian, this matrix of derivatives. And then we can ask about, well, if we take this perturbation of this form, and because we can write any perturbation as a sum of these modes, this is sort of the most general thing we can consider. And then this entire problem reduces to eigenvalue problem. And again, we have stability precisely if these eigenvalues lambda have negative real parts, because then the perturbations decay. And so we can just compute this Jacobian at each of these fixed points, calculate the eigenvalues. For the trivial fixed point, we'll see that it has a positive and a negative eigenvalue. So the dynamics looks like they're stable and unstable in one direction. For the other one, the eigenvalue is pure imaginary, which if you plug that back in and use something like Euler identity, you'd see that it's like oscillatory solutions, so it locally will look like oscillations. Actually, this system is very interesting mathematically because it admits a conserved quantity. And after some thought, you can arrive at this quantity. You can check that if you evaluate how this quantity changes along solution curves, along trajectories, then that will be zero. So that means that the level sets are orbits, and level sets of these functions are closed curves, and these are periodic orbits. And so if you have started some number of prey and predators, what you will end up doing is just oscillating around this equilibrium. The thing is, this is sort of made up. You could argue maybe that this model is, well, sort of structurally deformed so that you get this conserved quantity. That's very unlikely in general for dynamical systems to be true. But if you deform it slightly, you would either get convergence to stable equilibrium, or this equilibrium will be unstable, and often globally it will look similar. And then you can use something like Poincare-Bendixson theorem to argue that there will exist a unique periodic orbit. And so you indeed get this behavior even in more general class of models for predators and prey that there are these periodic orbits. So that's two species. Now let's go for arbitrary many species and see what we can do with that. So we can consider a model with as many species as we want. The FIs are the growth rates, and we can consider something like generalized Lotka-Volterra model. So again, constant growth rate, but then density dependent sort of interactions. The sort of diagonal terms in this matrix Aij describe the cell interactions, often called intra-specific interactions. That's the interactions you have with your own, with individuals of your own species, but then the off-diagonal elements describe in interactions between different species. And again, we can try to think about the fixed point. Okay, that becomes a bit harder, but probably still doable on a computer. You can sort of find the fixed point just solving this linear problem. If we are thinking about the non-trivial fixed point where all of these species coexist, then we can ask about the stability, compute this large matrix. And then we need to solve the eigenvalue problem and ask whether all real parts are negative for these eigenvalues. You can imagine that easily becomes a nightmare if you want to do it analytically for a fixed sort of interaction matrix. So maybe it's not a good question to ask about for a specific sort of very sort of detailed described matrix to ask whether the system is stable, but maybe it's useful to ask more generic question. And here comes the genius of Robert May, and he asked this question, and he calls his paper this way. Will a large complex system, large complex community be stable? And he asked about a generic system. What does that mean? Well, possibly, instead of thinking about a fixed matrix Aij, we could think about some random matrix. We could sample it from some probability distribution and then study the eigenvalues of that. you would firstly think that that will be even bigger nightmare, because now you be working not with sort of deterministic quantities, but with probability distributions. But it turns out that actually everything simplifies. To make it simple, think about sort of constant intrinsic growth rates, and then we will think about these competitions so that intraspecifically you would be competing at rate -1, but the competitions between different species are a bit weaker. They'll be centered around 0, but then there will be some sort of noise in how that happens. And so we'll be sampling these interactions from some random distribution with mean 0 and variance alpha squared. Now, you can argue that the fixed point looks pretty much like a vector of constant ones. To make it precise, you need to use something called cavity method. But if you think about it intuitively, well, you can try to plug this in. It reduces to this thing. There's this AII, the intraspecific competition that has 1 in there, so that goes away. And then it's just a sum of these alpha IHs, and then you can use central limit theorem. These are independent random variables, approximately goes to 0. So the next step, if we have this fixed point, we can think about the Jacobian, how that looks like, and will be looking like a constant -1 matrix, and then this matrix, which is a random matrix whose entries are independent, identically distributed random variables with mean 0 and variance alpha squared. And here comes a lot of work done in random matrix theory, pretty much originated in physics when people thought about sort of Hamiltonians, energy functions. If you think about energy functions, they are useful if you want to know sort of, for example, spectrum of hydrogen atoms. But often, if you have a complicated physical system, you don't know what your Hamiltonian exactly is. So you sort of consider random Hamiltonian, then eigenvalues, you need to know something about them, because these are sort of like the energy values. And you want to know something about how do energy values look like for a large random system described by this large Hamiltonian. And that's where it all originated. But Hamiltonians are sort of self-adjoint operators. They are symmetric. And so we can't reapply this theory because we have independent entries, not symmetric. But after some years of improving this theory, people derived this result. And this is the most recent one, is derived by a legend in mathematics, Terence Tao with Wu. And they are showing if you have a sequence of matrices of increasing size by S matrices with random IID entries with mean 0 and variance 1, if you consider eigenvalues of this matrix sort of rescaled by 1 over square root of S, then you can define empirical spectrum measure, sort of the distribution of eigenvalues, and then almost surely this measure converges in distribution to uniform distribution on a unit disk. So in here, I generated a random matrix of size 1000 and numerically computed eigenvalues. They are uniformly distributed on a strip almost. Now you can apply it to this to these large ecosystems, and what you'll see is that for large value of S, the eigenvalues have a uniform distribution on the disk. They centered around -1 and has radius alpha times square root of S. So that means that if this sort of interaction strength alpha and number of species is sufficiently small, then all of the eigenvalues are in the sort of negative real part half plane, and the dynamics is stable, otherwise it's unstable. And this is what famously May concludes in his paper. Roughly speaking, this suggests that within a web species which interact with many others, should do so weakly, and conversely, those which interact strongly should do so with but a few species. And so in stable ecosystems, all your interactions are either weak or are not with many species. This is the region where it's stable. Now we can go and think about microbiome. That's the bacteria that we all have in our gut. And people study stability of microbiome a lot. It has important consequences. If you have a stable microbiome, that means that if a pathogen comes into your body, you are much less likely to sort of allow this pathogen to grow because your ecosystem is stable and likely might be stable against invasions and other perturbations, such as, well, you eat something bad, causes a bit of inflammation, something. It still does not necessarily need to mess up your microbiome too much. So stability of microbiome is extremely important for our health. Now, people have studied how a microbiome, stability of microbiome works. And they constructed this experiment, in lab, where they took different isolates of different bacterial species, they co-cultured them and grow them also in isolate. By comparing these two, you can infer the interaction strength, and you can easily change the number of species that you put together to interact. And then you can measure the time series, what happens with them. And they done also some modeling, and they identified 3 phases. Phase 1, where all species coexist, that's the stable coexistence. Then phase 2, where they no longer coexist, and phase 3, where they coexist but fluctuate. The dashed line is the boundary derived by May. The second boundary comes from much more recent work, but again, random matrix theory, similar ideas, and you can see that you get these fluctuating phase. What is very cool that in the experiments they managed to reproduce these results. And so now we have empirical confirmation that this is indeed true, at least in the case of microbiome. Now, going to the work that is happening in our lab, we are very much interested in microbiome and its stability. And Kevin has been for many years now. And this is one of the sort of biggest success stories in the lab, where people thought about cooperation and competition in the microbiome. You can sort of think about how probability of cooperating in this network will affect the conclusions of these sort of arguments with random matrix theory. And what you can prove, the stability in here is just like minus a real part of an eigenvalue. And you can see that the stability decreases as cooperation increases. So competitive communities are much more stable than those that are cooperating. At least that's what theory suggests. Then Jake in our lab, he went and done pairwise interaction experiments with various isolates from soil, C. elegans gut bacteria, human gut bacteria. And you can see the red is the competitive interactions. They are much more prevalent. And that's actually the case as you are sitting in here right now, the bacteria in your own gut are in war with each other. They have many weapons to fight with each other. And I know it may sound scary, but it's actually beneficial for us because it makes the communities much more stable and it makes us possibly more healthy. Anyway, I think there's a this is really interesting area nowadays because it also asks questions that are interesting for mathematics. There's a lot of open questions around the matrix theory. And this is a question I haven't seen anywhere, but I'm personally interested in to see solved. Just imagine, so far people are considering independent variables drawn from the same distribution. But as I told you, the diagonal entries, these are self-interactions. These are intraspecific interactions, pretty much biologically different from the interspecific interactions we are having with different species. So far, how that enters the modeling is assuming that there's a different mean to these interactions. They are drawn from a distribution with a shifted mean, but the same variance. But what if the variance is different for the intraspecific and or for the intraspecific and interspecific uh, uh, competition coefficients? Mathematically, it's a question to ask if all the assumptions as in the Tau's theorem are the same, but we assume that the variance, that the diagonal entries have variance sigma, we can ask a question, how does that affect the result? And this is just a few numerical simulations. Actually, Summers showed that it doesn't really matter if you go to a limit of very large S. So as you go to large number of species, the theorem still holds. You'll eventually converge to this circular distribution. You can probably argue that if you go to very large sigmas, it will eventually be the large entries will be just on the diagonal. These will eventually dominate the distribution of eigenvalues. And so probably the distribution of eigenvalues will just look like a distribution of real line given by the distribution of the diagonal entries. But what happens in these intermediate regimes? Can we get an idea what are these sort of curves that, well, regions that support the distribution of eigenvalues? And then we can ask a lot of questions about how sort of variance in intra and interspecific competition affects the results. Anyway, this brings me to the very last part of my talk, and we will be chatting about spatiotemporal dynamics. Now we thought about one species, more species, many species. What happens if we put space in there? And this brings us to the idea of the Turing mechanism. So we can have a model, which is a model of temporal dynamics, and we can assume that it admits a unique stable fixed point. And then we can generalize it and think about a spatiotemporal model, where we, in addition, assume that there is some diffusion happening. And so if we think about it, just a diffusion to this model on some infinite line, the steady state that this temporal system admits will be still a steady state of this dynamics. And we can ask whether adding diffusion makes it more stable or less stable, or what happens with the stability. So this is sort of like homogeneous distribution of the stuff. You have a bottle, put some possibly chemicals in there, you have them homogeneously distributed, ask whether that's stable. Diffusion in general is stabilizing. So if you have stable plus stable, you would think that it's stable. But the interesting thing about Turing instabilities and the great idea about them is that stable plus stable is not necessarily stable again. If you do the analysis, you can again take perturbations, linearize the dynamics, get something like this. Think about appropriate modes, turn that into an eigenvalue problem. In the eigenvalue problem, we get the Jacobian of the temporal system minus this matrix. If we have just one species, chemical species, or now it can be biological species or anything, then diffusion is stabilizing. And that's what people have always thought. And then Turing came, well, just because this eigenvalue now is the previous eigenvalue of the temporal dynamics, that's negative, so it's more than zero stable. Then Turing came and asked, what if we add two species, will this still hold? And actually, it's just this very special case when you have one species, when adding diffusion, the diffusion is stabilizing. With two species, it's not necessarily true. We can do the analysis. We can think about this Jacobian. The entries can be represented in terms of trace and determinant. And you can easily check that they have negative real parts precisely when trace is more than zero, determinant is bigger than zero. What happens is you consider now trace of this thing. If you consider trace, it amounts to trace J0 minus k squared d1 plus d2. And so that is negative because trace of the original matrix is negative. The temporal dynamic stable, adding something negative makes it even more negative. So the only way how it would leave the stability region is by if the determinant becomes negative. And you can just compute it, determine, you can realize that it looks like a quadratic function and that it indeed can become negative provided this condition is satisfied. And then there will be an appropriate regime of these wave numbers k that describe different modes. And in this regime, you would observe diffusion-induced instability. If you think about what this condition mathematically means together with the stability of the temporal dynamics, you can realize that the diagonal entries and the off-diagonal entries in the Jacobian must have opposite signs of the temporal dynamics. And so there must be a plus-minus interaction between these species. And the second condition is this sort of condition you obtain on these diffusivities. And the diffusivity of the sort of inhibiting species must be much faster than of the activator species. You can also think about it that there is a bifurcation as motilities pass through this line, and as you go through this line, the homogeneous steady state gives its stability through transcritical bifurcation, usually to the Turing pattern. So now let's go more in back maybe to chemistry, to biology, thinking about where we can see these Turing patterns. So let's think about something simple, two non-living things, chemical and chemical. Yes, we can, if there's positive, negative interactions in the chemical reactions, we can get the result that there should be patterns, and indeed we can see them experimentally with appropriate chemicals. And it has been suggested that these distributions of these chemicals can serve as pre-patterns that determine pigmentations of cells during development, for example, in zebrafish, then determining the patterns and spots on zebrafish. Possibly, we could maybe use it to explain also sort of patterns on coatings of other animals, such as cheetah. There's an interesting thing I told you with that you need appropriate range of wave numbers where the instability occurs. What that means that if your domain is very small, you might not be able to fit a wave into it. And so there is a necessary condition of at least some sort of sufficiently large length scale in order for instability to form. And to prove it more mathematically, you need Sturm-Liouville theory, construct appropriate basis of eigenfunctions, but that's sort of the argument. The thing is with cheetah that in here on most of his body, he has two dimensions where you have sufficient length scales and the instabilities can form. But if you look at this at the tip of the tail, you just have one long dimension and another short dimension. What that means, the instability can form only in one dimension, and you get stripes instead of spots. Okay. This is a lot of things Philip, my other supervisor, has always been interested in. And so you can go and think about other examples. This is very current topic. You can think about vegetation and nutrients, plus-minus interaction again. Vegetation eats, consumes nutrients, and nutrients gives rise to growth. And if you are in semi-arid environments, you can observe these Turing patterns if you take a drone or something. And people have reproduced this. Oh, sorry, definitely. This is, well, in silico often means, usually means in computer, because, oh, yeah, because of the materials we use to produce computers. Or I meant in here mathematically, we have a mathematical model. In vitro means experimentally, in control laboratory settings. In vivo means, well, usually in the context sort of trying it in alive individuals, or in you could, in here I also needed this in the field. Yeah, I could have changed these words, sorry about that. We can do the same thing. Instead of plants, we can take bacteria. This is again a work from my supervisor, Kevin Foster. Nutrients, bacteria, same thing you can get during patterns. Well, in natural environment, hard to say. but it's probably just because we can't really observe bacteria in natural environments. We usually need to take them back into the lab. Now, here comes an interesting question. And I think something where I want to make the message that as mathematicians, I think we should often be humble about limitations of our models, because this is an area where people thought predator-prey plus minus interactions. We talked about it, and I showed you on the left side, you saw that there can be a stable temporal equilibrium, and then people try to argue that there can be, if that is the case, you have the stable temporal dynamics, then there can be Turing patterns. This is a work by Jim Murray, a sort of supervisor of my supervisor in 1977. And from there, people have been publishing about this pretty much almost every other year in the mathematical field, arguing that there'll be predator-prey Turing patterns seen in natural world. Despite that, and despite that people tried in 90s, we haven't observed them. People thought about plankton, collected data about plankton, thought about plankton patchiness of fine scales, when maybe all of the sort of oceanic flows will not affect it. The distribution will be just due to biotic interaction. Eventually, they found out it's more like very directed movement of plankton that causes these patterns, not the Turing mechanism. So possibly there's a good reason why they do not form. And this is, well, this is an idea of my work that I have published recently, and you can also read online. The idea is maybe, well, we shouldn't just be thinking about ecology. Let's bring evolution into play, because there's this condition of motility, and maybe there might be a good evolutionary reason why motility is not in the appropriate regime for Turing patterns to form. For that, we need a model of ecology and evolution. Because I work a lot with bacteria. In bacteria, you have ecology and evolution interacting a lot. With bacteria, there are similar timescales of evolution, of genetic change, and ecology, and you often need to take into account both. So this is my work on antibiotic resistance, and mathematically how you do it is that you consider spatial dimension, but you introduce another independent variables describing phenotype or genotype, in this case, antibiotic resistance, and then you study the dynamics in there. If you want to read a bit more about antibiotic resistance evolution and modeling of that, there's a link to the paper. But we'll use the same idea now for predator-prey systems. So this was the original model, diffusion, sort of random motility of predators and prey. And then we'll couple it to evolution. So we need to modify this model. We add another variable of independent variable phenotypes with motility, the IP. And then the modified model for the spatiotemporal dynamics is this one. And what we get is, well, the same model, just now the growth rates are proportional to the total number of species irrespective of their phenotypes. We need to introduce evolution. How we do it is that we have a set of phenotypes that will be updating. We'll introduce the processes of natural selection, sort of removing phenotypes that went extinct and whose density is very low, and introducing mutations, introducing sort of new phenotypes of relatively nearby diffusivities in this case, to those that are possessed by surviving phenotypes at low density. Now you can try to run this. So these are similar plots as you saw for the antibiotic resistance. Now you can see this sort of spatial patterns in prey and predators, their abundance. This is the motility dimension, phenotypic dimension, and this is the spatial dimension. Now this is the plot where I'll be showing whether you are in the regime to form Turing patterns or not. And then I'll also be plotting the sort of total reproductive rate of a given species, so either of predators and prey. It's sort of like a overall measure of the fitness for the entire species, and then I'll be plotting the total abundance. So let's see what happens. Initially, indeed, Turing patterns form, and that's just because the ecoevolutionary model just reduces with one phenotype to the spatiotemporal model. But what happens next? Okay. Yes, this is what happened. Well, yeah, sorry. During patterns form, the thing about it is, however, that the fitness went down. And you can prove mathematically that if you have a steady state that is not homogeneous, then the total fitness of both species will be suboptimal. Intuitively, this is because that if you are moving randomly and you are prey, you are very likely to go into regions where there is more predators. You don't want to go there. It's actually better for you not to move there. Similarly, for predators, if they move randomly very much, it takes them into regions where there is not any food, no prey. That's not beneficial for them. That's sort of why they decrease in fitness. If in this hypothetical scenario where Turing patterns would form, and how they respond is that they do not move that much. Firstly, prey loses the motility. Secondly, predators lose their motility. You can, yeah, and eventually both of them lose their motility if we assume that there was a Turing pattern. What this sort of means is that the motility decreases, that changes the patterns along the process, and you can study it with a framework in mathematical biology called adaptive dynamics. You can think about a population of sort of residents, just the model as before, spatiotemporal model. You reach an equilibrium with fixed motility of predators and prey, and then you introduce an invader of, say, prey of low density, and you ask whether this invader will be able to invade or not, increase in density or not. And you can show that if pattern forms, always invaders with small motility will be able to invade. This is not a coincidence. You can prove it mathematically. It goes into a bit of linear stability analysis, where now your sort of Jacobian is spatially non-homogeneous. So you need to use some mathematical tricks, but you can sort of prove that if you have a positive stable spatially inhomogeneous steady state, there's a Turing pattern, then if you introduce a mutant of different motility, it will always be able to invade if it's of smaller motility. In particular, Turing patterns are not evolutionarily stable if smaller motility phenotypes are present and motility can evolve. So what happens after that? And this is really interesting. What happens is that the dynamics goes into a regime where homogeneous steady state should be stable, but instead, because evolution already introduced a bit of phenotypic heterogeneity, there are phenotypes of various motility, you can see an induced predator-prey cycles and predator-prey waves. These are sort of predator-prey waves of completely different origin than you can see in the Lotka-Volterra model, where they appear already at the temporal scale. In this case, the temporal scale, there should be a stable equilibrium between predators and prey, but differences in their motility can destabilize it. And such predator-prey waves are evolutionarily robust. And so, yeah, you can prove it analytically and find regimes that indeed, if you have slow and fast predators, they can lead to these predator-prey waves, which brings me to our very last idea, which is traveling waves. And these are very much prevalent in biology, and we can understand them mathematically. If we just, again, think our simple logistic model at diffusion, and then we can see that there will be solutions that will look like waves. If you plug that in and linearize at the front of such wave, you get this equation, then you can sort of, because it's a linear equation, try to solve it. This is C is the speed of the wave, and you can see that there will be waves of speed bigger or equal to 2. And with a bit more of theory, you can actually prove that the lowest speed is the one that any sort of initial condition with compact support will eventually approach. And so C equals 2 is the speed of the emergent waves. And we can see these waves in biology, and they are prevalent across scales. So if we think about tumors, and tumor invasion as the tumor expands. And there's a lot of work happening there, pretty much in the Wolfson Center of Mathematical Biology with Philip and primarily Helen Byrne, who is a professor of mathematical biology. They're focusing on cancer, thinking about how all of that plays out. And you can use these sort of ideas about traveling waves to study cancer and cancer invasion. Similarly, you can use it in ecology, and you can study how invasive species spread through ecosystems. So this is work by Philip in 1990s, when in the UK we had gray squirrels and red squirrels. Gray squirrels were introduced; they were invasive, and well, he managed to produce a model that shows that as time goes on, the gray squirrels will replace the red squirrels, which is pretty much what you can see if you come visit UK now. And so maybe just a very last comment on this, an interesting fact. Philip came very excited to me a few days ago saying, oh, maybe it relates to your bacteria as well, because now there's a recent study that suggests that the stability of their microbiome in the gray squirrels is the reason that makes them competitively more advantageous. So yeah, so it's all very much connected, and I think quite exciting, and I want to thank you for your attention.
I would like to thank Vitek for his nice and interesting talk. I hope that all of you, including mathematicians and biologicians, enjoyed it. And my question is, does anybody have some question or remark?
You don't need to be scared.
Okay, so I have maybe one question.
Yeah.
I'm biologist, so I don't pretend that I understand all of mathematics which you explained to us. However, you actually show us that for some biological problems, you're able, even if on the first place you don't have mathematical solution, you can try to find some kind of solution, of mathematical solution of these biological problems. I wondered if it is possible, if you find such solution, or at least the procedure how to get to this solution, is this solution applicable to some clear mathematical problem then that you are inspired by biology and try to like somehow use it in some different mathematical problems?
That's a great question. I'm trying to think of a good story, because I think there will definitely be examples of that. I think with the last story of traveling waves, there has been a lot of research done into what these traveling waves are mathematically, why they are stable, what does it mean for a traveling wave to be attractive or to be sort of attractor of the dynamics? How can we go about proving this? And so I think there is quite a large area of mathematical theory that sort of, but I think it's more likely that there will be, by some biology, we will have a new mathematical theory being developed. It might take a few more years to actually use it in some other field of mathematics to be useful across mathematics as well. And I think we could find examples, but none is coming to my mind.
Thank you. Some more questions? Wait until the microphone.
Hey, it's just a personal question on the way you work as a mathematician working in biology. Do you normally find yourself looking at the biological landscape and trying to find interesting problems that haven't been solved mathematically yet? Like looking for the mathematics in the biology, or more the other way around? Like you look for biological problems that have significance and you try to model them and just see what happens.
Yeah, that's a great question. And I think it's sort of a gradual progress. When I first thought about biology and mathematics, I was pretty much in a stage when I was super excited about mathematics. For me, biology was just a place where I could find some nice mathematics, and I tried to explain the evolution of why cicadas have prime number length cycles with group theory, and I thought, wow, that's interesting to think about the group theory, and this biology is just sort of the rest. But over time, I think I changed this perspective completely, and I realized that it's often exciting to try to follow what you actually see in the biology. And then if you have sufficiently many mathematical techniques, you will often be able to find, with a bit of luck, something that is both mathematically nice and and describes the biology. But I think it's much more useful, especially for the biologists, because otherwise you are doing just mathematics, which hardly translates to the world of biology. If you actually start in the biology, try to think about the problem, what is needed in the biology to be solved, and then try to use all the fancy techniques you have to get to that result.
Just one more small question. Is there any like big mathematical biology question that you find yourself thinking about? Like the big problem, what would be the, one of the 7 millennium problems in that region?
Or that's a hard one. Oh, I think that's actually what I learned when I came to biology. It's not like in mathematics where we make our Hilbert lists of several problems that we need to work on. And biology is much more creative field, I think. You come into it, you think something is exciting and you start working on it, or something is somehow useful. And sort of biology is very natural in this way. It sort of comes and goes. And I definitely have my personal favorites, but I don't think these are like the biggest problems every biologist would accept. These are the biggest problems. So my personal favorite is thinking about decision making in biological communities and organisms, both with bacterial scales, how you eat different nutrients. Do you decide to eat this source of carbon or that source? Will you eat them both together or not? Or decision making as you move as an animal. Do you go, if I see targets, do I go straight to the target, or do I go in the compromised direction? And once they are very close to me, I decide. That sort of decision-making problems in biology, I think personally interesting to me and not much studied until now. But yeah.
Thank you. So some more questions? So it seems that you understood everything. So it can be something like a problem on the next Waikiharni competition if you will come next year. Everybody will have 10 points from it. Okay, so I would like to thank Vitek once more. And I have two organizational announcements. So first, while we are enjoying this talk, so your teachers, your delegates are working hard, and you can see on the internet some preliminary results. When I came here, 3 problems were corrected out of 8, so maybe now it's more. And the second announcement is that the banquet is open now. There's plenty of food there, so you are welcome, and I hope that you will also enjoy it. So, thank you.